This video is going to detail the concept of aromaticity, but before we get into that, let's review a little bit about the concept of delocalization. Delocalization we saw essentially as resonance structures, right, where we didn't see a localized positive or negative charge stuck on a single carbon. We can use pi electrons to an sp2 carbon to help stabilize that charge. So in this case, we have a double bond and a carbocation on the next position. We can move that double bond to have a positive charge on the other carbon. So realize this is more stable than a traditional carbocation because it is not stuck on a specific carbon. So what this species really looks like is a partial positive charge on one carbon and a partial positive charge on the other, meaning rather than having one carbon stuck with all the burden of a positive charge, it's split between two. This is a really important concept to understand aromaticity. This is the advantage of this. So you can still move more than one double bond, meaning if we have a conjugated system here with our double bonds one position away, we can move that double bond one time, we can move the double bond a second time, and just like in the last example, this positive charge is no longer localized on one carbon. It is now delocalized among all three that have that positive charge in the top structure. I'd encourage two examples that we talked about before were the allylic carbocation and a benzylic carbocation. And both of these are examples of more stable carbocations because they are delocalized. I'd encourage you to try to be able to draw some of these resonance structures for a benzylic cation. Try pausing the video now. Okay, you should be able to draw arrows for this, starting with whatever double bond you can move out towards the positive charge. Whatever carbon is being broken from a double bond will now have the positive charge, and you can just move right around in a circle, alleviating the positive charge until it's separated or spread out onto every position. So as you can see here, on a ring, we have a lot more flexibility in order to spread out that positive charge, lots of pi electrons to go around. This leads us right into aromaticity. And often the best example to help explain it is the use of benzene. And I've drawn benzene on the right there with having 3 pairs of pi electrons, meaning every carbon is sp2 hybridized and every carbon is in conjugation with each other. And this concept of aromaticity essentially means turning a 6 individual p orbitals into one pi electron cloud. And you can sort of see like a ring. So in order to be aromatic, we're going to say that it needs to be an uninterrupted cloud of pi electrons, meaning we need it to be cyclic, planar, and every ring atom must have a p orbital. The pi cloud must have an odd number of pairs of pi electrons. Another way to explain that is that the total number of electrons needs to be 4n plus 2, with n being any whole number integer. So you can use either one of those bottom 2 rules to figure out how many electrons are in your system. Let's look at some examples that are not aromatic. Here we have a cyclobutadiene. This one, every carbon is sp2 hybridized. We have a ring, but unfortunately here this does not fit our odd number of pairs or our 4n plus 2. We have 2 pairs of electrons in even number or a total of 4 pi electrons. That's not going to fit either rule. So since it has an even number, it is not aromatic. Cyclooctatetraene. Here we have, again, 4 double bonds, meaning an even number of electrons. In addition, at this point, pretty much anything between 8 and 11 carbons sometimes is tough to get to be planar. So these p orbitals do not overlap. So this has an even number of pi electrons, and it is also not planar. Let's look at some other examples. Here we have cyclopentadiene. Again, every atom in the ring must be sp2 hybridized, so This is not aromatic because of that sp3 carbon. The cyclopentadienyl cation, not aromatic again, even though that carbocation is sp2 hybridized. We have 4 pi electrons, or still an even number of pairs. Here we have the cyclopentadienyl anion, and for this purpose you're going to see negative charges. Remember, we always show them as a lone pair of electrons. In this case, we have a cyclic system, we have a p orbital, and we have 6 total electrons, 2 from each bond, or 3 pairs of electrons, odd number. And you should be able to draw out the resonance structures for this, showing how the negative charge is now equally split up between every carbon in your structure. If it's a heterocycle, meaning if it's an atom that's not carbon, you can still allow one of those electron pairs to be placed in conjugation. Remember, delocalization means this has resonance structures that involve having a double bond placed on the oxygen. So here we can have a positively charged oxygen, meaning that bottom one in all of these resonance structures on the right, where we would turn that oxygen from sp3 into sp2. So those contributors allow delocalization to take place. In general, if you have a double bond to a heteroatom, in this first example on the bottom, you're already sp2 hybridized. So you don't need to worry about, well, is that lone pair participating in the ring? It doesn't matter, because that nitrogen is sp2. It has a p orbital already in conjugation with the ring. The other 3, whether it's a nitrogen, oxygen, or sulfur, those have resonance structures to allow the double bond to be placed with that atom, turning it into an sp2 hybridization, similar to the resonance structures you see at the top with oxygen. Using the 3 types of criteria, cyclic, planar, and follows our Huckel's rule, decide which of the following are aromatic. Please pause the video now. Okay, starting from the top. On the top left, every atom is sp2 hybridized. However, we only have a total of 4 electrons, so it cannot be aromatic. The next one, same thing. We already talked about this one. This one only has 4 pi electrons, meaning it cannot be aromatic. The next one, we have a total of 6 pi electrons, so we're looking good. It is cyclic. Every atom is sp2 hybridized because of the carbocation, so yes, this one would be aromatic. The next one, we have a total of 1 double bond, meaning an odd number, or a total of 2 electrons. If we make our integer 0, 4 times 0 plus 2 is 2. The top carbon, since it's a carbocation, is sp2 hybridized, so yes, this is also aromatic. On the next row, here we have a total of 4 electrons. Again, that's a problem. In addition, here we have an sp3 carbon that is next to the carbocation, meaning it cannot be aromatic. The last 3 are all aromatic. Remember your rules. If the nitrogen or heteroatom is participating in a double bond, you are not going to include it having pi electrons, because its pi electrons are already in the ring, making it sp2. So we have a nitrogen participating in a double bond, meaning that double bond counts as 1, the double bond up top counts as 2, and the lone pair from the nitrogen has resonance into the ring, giving it its 3rd pair. 6 total electrons were set. Same situation for the next one on the right. We have 2 from each of the nitrogens involved in double bonds, as well as the double bond involved from each carbon, total of 6. You can have systems that are more than 1 ring, as long as they continue to fit into the 4n plus 2 rule. That is aromaticity.